You must know physics to watch Oppenheimer. Or must you? I finally managed to watch Oppenheimer on the IMAX screen, and boy, was it a delight. Yes, and like many of you, I had also heard that one must know physics and quantum mechanics and whatnot to make sense of Oppenheimer. But then I thought, this film is neither called The Atomic Bomb or The Manhattan Project or even the Los Alamos Lab. It's called Oppenheimer, which meant that it must be about the man, not his creation or the project. And you would be right to think the way I did. But again, having an idea of the physics and the timeline of what happened before Oppenheimer will help make most out of the story that the film narrates. And this episode is just that. It's about what happened before Oppenheimer, the story. And don't worry, there are no spoilers here. Actually, if you think about it, I cannot possibly give you any spoilers in this except for the last scene maybe, because this film is strongly rooted in the history of the atomic bomb and that of the World War II. In fact, almost half of the film is made up from actual transcripts of hearings, one related to renewing Oppenheimer's security clearance, and the other a Senate hearing, about Louis Strauss. While the rest is derived from a biography. The film tries to depict the complex person that Oppenheimer was, the circumstances that existed then, and some of the crucial aspects of the war that led to what happened. And I cannot think of anyone other than Nolan who could do justice to the story of a man as complex as Dr. J. Robert Oppenheimer. Of course, the film does not do justice to the others that significantly contributed to the scientific research behind it. But then again, the subject of the film is not nuclear physics, and a 3-hour biopic can do only so much justice to the subject. I personally would have probably liked it to show the other contemporaries who contributed to the project a little more, but then overall, I really don't have much to complain about. The other point that I wanted to mention was that I'm not a Nolan fanboy and this is not a film review. So, so keep that in mind when you listen to this. Now, let's start with the scientific background. Knowing a little bit of physics will help you make your watching experience a little bit better. So here I am giving you just enough of the science in the film. And don't worry if you're not from the science background. This is just high school stuff. You've read or studied this already. I'm just recapping it for easier recollection and some context. So let's set the stage. Imagine yourself in the late 1800s and early 1900s. Einstein had published the special and general theories of relativity, in that order, in the first 2 decades of the 20th century. The world of physics and chemistry are buzzing with discoveries. But in the interest of your time, I am going to limit these inventions to a small subset with a handful of people who were crucial to the development of the model of atom and the atomic bomb. Now, let's start with the early days of the atom. You know, atoms make up all matter. It actually reminds me of a wall mural that we have in our office that says, "Don't trust the atoms. They make up everything." Well, it's a good pun. From the air we breathe to the lava that flows down volcanoes to the cells in our body, everything is made up of atoms. Atoms as a concept, though, not really new to us. In fact, we have been talking about atomos for a few millennia now. Although nobody truly knew, or I could probably even say knows, what an atom looked like. Partly because the atoms are really, really too small. What do I mean by that? For us to be, able to see something, light must bounce off of it and hit our retina. This basically kicks off a chemical reaction in the retina, which creates a signal, an electrical signal that the optic nerve carries to the brain. But when we try to see a particle that's hundreds of times smaller than the smallest wavelength of the light we can see, well, how can we do that, right? Which is why we must resort to observations in ways other than directly seeing these particles. And this is where J.J. Thomson comes in. So let's begin our journey with the cathode ray. This ray was discovered sometime in the mid-19th century. I'm not a historian, so I don't really remember the exact dates. These probably should be available this should be really handy. So anyway, I was a little lazy to pick them up. J.J. Thomson was the first one to study these cathode rays further, and he concluded that these were negative corpuscles because they got attracted to positively charged plate placed on the other side of the cathode ray tube. Not only that, he also noticed that these rays could be deflected by an electric field in the sense that the negative terminal of the electric field, or let's say a negative plate, repels these rays while the positive ones attract it. Now, next thing he did was fill the cathode ray tubes with one gas or another, and he noticed that the type of gas did not really change the nature of the cathode rays. Now, given that cathode rays were really lighter than anything known until then, the conclusion that he came to was that this constituted something that was part of the matter. And this was something that was present in all matter. In other words, he thought that this was a corpuscle that was part of an atom, and this was present in all atoms. These negative corpuscles would later come to be known as electrons. Now, more experiments were carried out with in which these electrons were stripped from matter. What remained was something that was a lot more massive than electrons and was positively charged. So Thomson said that atoms must be like pudding, which is uniformly positively charged, making up most of its mass, while electrons were like raisins scattered in the positive electric field. Very delicious. Next came Ernest Rutherford. He was J.J. Thomson's student, and he did some more experiments to understand the nature of atom. Rutherford was a contemporary of Marie and Pierre Curie, the ones that discovered radium. So radioactivity was all the rave during their time. So there was enough evidence that some elements, they naturally emitted some radiation. Rutherford subjected these radiations to an electric field, and he found two types of rays. One was alpha, the other was beta. He just called them A and B rays, basically. And these were the rays that the radiation split into. Now, the alpha rays deflected towards the negative terminal or the negative side of the electric field, and the beta rays towards the positive. And Rutherford concluded that alpha rays were positively charged while the beta rays were negatively charged. He also noticed that the beta rays were very similar in nature to the cathode rays. Later, it was found that beta rays were indeed like cathode rays because they were also high energy electrons, nothing else. And alpha rays were later found to be positively charged helium or helium ions. This meant that alpha particles were massive compared to the beta particles and were also much bigger. Rutherford then set up an apparatus that bombarded a thin gold foil with alpha particles. He expected that the alpha particles would probably slow down a little bit but pass straight through and hit the photographic plate that he placed on the other side. This was because, based on Thomson's model, a gold foil should mostly have positively charged massive atoms with electrons scattered in them. Now, since there was no positive charge concentrated anywhere specifically across the foil, the beam should pass straight through. But when his proteges, Hans Geiger, you might have heard about the Geiger counter, so that's named after Hans Geiger, and Ernest Marsden performed the experiment, they found that some alpha particles ricocheted and way too many rays deflected more than 2 degrees, which was a lot. And that made Rutherford conclude that atom was not like a raisin pudding. He said since most particles passed right through the foil, the atom must mostly be empty. But at the same time, since there must be something heavy in the atom which is making the alpha particles ricochet, because remember, the alpha particles were massive. This meant that there was something very dense within the atom, dense and positive enough to deflect massive alpha particles, and an electron would just not cut it. Now imagine this, or think about this. Like charges repel, so anything positive coming near another positive particle is going to repel. So that's why he concluded that the center of the atom must be something dense and positive. So Rutherford came up with his model of atom, in which he said the nucleus, that's what it was called now, contained all the positive charges, protons essentially, but they were not called that yet. They were packed in a small space, while the negative charges, which were electrons, made up the rest of the atom. Kind of still like the Thomson model, scattered across the atom. Then came Niels Bohr and Werner Heisenberg. First Niels Bohr, I guess, if I remember correctly. Now, Rutherford's model answered some questions that were left unanswered by the Thomson model. But then there were still other questions about the atom, like how come the electrons, which were negatively charged particles, did not get attracted to the proton-filled positive nucleus, and, well, the atom did not collapse or implode. Now, quantum mechanics is what comes into the picture around here, but we don't really have to get into this now because this is not relevant to the movie. Niels Bohr proposed his model using the principles of quantum mechanics, to which Werner Heisenberg's and others' wave mechanics were added, and that gave us the atomic model that we have of today. Now, the interesting part here is that Robert Oppenheimer was somebody who, under Max Born, studied quantum mechanics, and he kind of really mastered it. This will not really feature in the movie, but kind of feature there. And again, this is not really significant to the story. Actually, it's just just something in the background that's happening. Well, then came James Chadwick. Now, we must note by this time we had a solid understanding of how to calculate the mass of atoms. I know that it kind of sounds nuts, but it's true. We had Avogadro and the likes by this time. And some scientists did not quite buy into the idea that atoms were only made up of protons and electrons. Chadwick was one of them. You see, any stable atom is electrically neutral, which means there are as many positive charges in an atom as the negative charges. For example, hydrogen has one proton and one electron in it. Helium has 2 protons and 2 electrons. Going by that idea, there are only protons and electrons in the atom. It would mean that one helium atom weighed twice as much as a hydrogen atom. But in reality, a helium atom weighs 4 times as much as the hydrogen atom. So experiments were performed to find out why, and James Chadwick concluded that there was another class of particles within the nucleus, which was electrically neutral, but it weighed almost as much as a proton. And this particle later started being called neutron because it was electrically neutral. And this neutron is critical to the atomic bomb. Next comes radioactivity. Radioactivity until now was thought to be a passive process. In this process, large unstable atoms with large unstable nuclei decayed, quote unquote, as in they kind of broke down by releasing particles and tried to become more stable. This was kind of different from what we had believed until then, which was that the atoms cannot be broken down or added to. We had evidence for, say, one atom of radium emitting one alpha particle to reduce to radon, which is an inert gas, which doesn't react with anything. Basically, that's what it means, an inert gas. Now, this process happened naturally, given that an alpha particle, a helium ion basically, was being released from uranium to make thorium, for example. It followed that heavy, unstable, and therefore radioactive elements could split their nuclei and therefore the atom and form 2 or more atoms. Let me put this again, in different words. Let's say that you have taken a big unstable atom, right? It can basically emit one, say, alpha particle and then become a smaller atom, and then emit another alpha particle, become a further smaller atom, and so on. This was possible. Just like alpha particles, though, they could emit beta particles or neutron as well, or a combination of them, and become a stable nucleus. We also found that this decay also released energy, and this is critical. For example, or one example of this energy being released was the gamma rays being released as part of the radioactive decay, which was not found by Rutherford as such. It was found by somebody else after a while, after a few years or something. But he called it gamma rays because, alpha, beta, gamma. Even though gamma rays were not like any subatomic particles, unlike alpha and beta. Anyway, not important again. Next comes radioactive fission. Now, we saw that radioactivity was considered passive, but that was only until Otto Hahn, Lisa Meitner, and Fritz Strassmann performed their experiment in nuclear fission. They split an atom forcefully by injecting neutrons into it. This was a groundbreaking discovery, which changed the world forever. This meant that one could take any sufficiently large atom, bombard it with one or more neutrons, get the neutrons absorbed into the nucleus, making it further unstable, and split it into relatively more stable, smaller atoms. And of course, release subatomic particles and energy in the process. When you go watch the film, connect from here to the scene in which Alvarez runs out of the salon. And given that every fission also released energy, it would mean that by breaking elements such as uranium and plutonium, we could create energy. While every fission only, released a tiny bit of energy, a large number of fissions could release a significant amount of energy because the energy added up. And this is the basis for nuclear reactors and nuclear bombs. So let's look at an example of how a nuclear fission bomb works, right? You take one uranium atom and bombard it with one neutron. The uranium atom splits into thorium and helium, for example, and releases energy plus 3 neutrons. Then bombard these 3 neutrons into 3 uranium nuclei, and that creates 3 times as much thorium and helium, and releases 3 times as much energy and 9 neutrons. Bombard these 9 neutrons or 9 nuclei with these 9 neutrons, making 27 times as much helium, 9 times as much helium and thorium, and releasing 27 neutrons. Bombard 27 uranium nuclei. Well, basically this goes on like this. So this will make the reaction go from one nucleus to 3 to 9 to 27 to 81 to 243 to 729 to 2000 plus, then 6000 plus and 18,000 plus, and so on. This basically creates an exponential runaway chain reaction. And that would release an enormous amount of energy, several thousands of times in magnitude, as seen in any chemical reaction. One point that is critical here, pun intended, is the critical mass. Roughly, this talks about how much fuel you need in terms of the mass enclosed in how much space, as in the volume. So the denser you make the fuel, the more effective it'll be. Because the atoms are packed closer together, the chances of neutrons hitting these nuclei is much higher. Now, that's all the scientific context you will need to watch the film. The rest will be shown on the screen, so you can go watch it. But let's not stop there. Let's also give you a little bit of an idea of the politics of the time and the war situation that existed then. So stick around for a bit more and get a little bit more idea. Now, in the 1930s, Hitler's forces had started on their capturing spree. A full-blown war had not yet begun, but there were signs of it. Finally, in 1939, the Second World War began officially between the Axis powers, which constituted the Nazi Germany, Italy and Japan, and the Allies, which was Britain, France, and so on. The United States was not part of the war just yet. Many of these brilliant minds in the scientific community in Germany were of the Jewish origin at this time, including Albert Einstein, Leo Szilard, Lisa Meitner, and so on. They were now being targeted by the Nazis. Out of fear, these scientists fled Germany to other places such as Britain and the United States. Einstein, for example, went to Princeton in the United States. Some scientists did try to raise their voice against the persecution of the Jews, and one of them even met with Hitler to talk about it. Hitler just said that he was not against the Jews, but just against the communists. But we all know the reality, whether the targets were identified by the ideology they followed or their origin. To the west of quote-unquote the pond, the United States were going through a tough time of their own. Their economy had taken a blow because of the Great Depression, and people weren't really very happy with their lives. But in general, the American sentiments were against the Axis powers, and the politicians of the day were well aware of this. On the European front, the Soviet Union was initially on the side of the Nazi Germany, but when the Nazi forces started advancing into the USSR and taking over their territory, they switched sides and aligned with the Allies. In general, the binary in Europe in this war was fascism versus communism, with people opposing the Nazi actions, believing that communism was the only answer to the fascism that the Nazis were engaging in. But when you watch the film, remember this: the sentiment in the United States was aligned against fascism, but it wasn't necessarily aligned with communism. That distinction is important. Fascist versus communist is a false binary in the context of the US. Also, remember that the Democrats were running the administration in the US at the time. It was a kind of a complicated soup. So yeah, when you watch the film, watch it with with that lens, because that'll be important. That's when it'll make more sense. Now to the war aspect, right? On the Asian side, Japan was advancing westwards and southwards, basically towards China and towards Indonesia and Java, Sumatra, and those places. Tensions were rising between the United States and Japan through the Great Depression. The US did not like that Japan was forcefully annexing territory and engaging in atrocities against civilians. The United States have always considered themselves flag bearers of the free world, and they had been allies with the likes of the Great Britain. Wait a second. Does anybody see the irony here? Well, anyway, Japan's aggression against the interests of the Allies did not go well with the United States. So the United States were not part of the war for the couple of years after it began, although they were lending weapons to the Allies, whatever that meant. The United States had also imposed sanctions against Japan, and they had started supporting the resistance to the Japanese expansionism. This made Japan angry because it saw these actions as Western interference in Eastern matters. Okay. Anyway, one early morning, I think, Japan bombed Pearl Harbor out of the blue. They said the surprise element was the only edge that they had over the US. Of course, the US saw this as treachery. This pulled the United States into the war. I mean, when I chuckle, I don't mean to chuckle at the war. It's just I'm chuckling at the responses that these countries and the politicians and who not give, because, well, war is terrible. A few people's decisions have serious repercussions to hundreds of thousands or millions of people. So yeah, I'm not really in support of wars in any way. But anyway, so there's also always this political angle in a democracy. Public sentiment is of utmost importance to politicians. Janta Janardhan. The American people, of course, must have felt really violated when Pearl Harbor was bombed like it was. It was a terrible act, if you ask me. And if I remember correctly, there were 2 waves of attacks, even, not one. So that. And the US were also considered a strong power globally. So Japan's bombing of the US was a direct blow to that image as well. The US keeping quiet after such an attack is anyway unthinkable, even today. So that, right? And third, meanwhile, the American intelligence agencies have also learned that scientists working under Hitler were working on a nuclear weapon. How could the US not do anything? Well, anyway, 3 years or so later, right before the Trinity test could happen, Hitler had killed himself. Within days, the Nazis surrendered. Why did the US not scrap the Manhattan Project then? Well, 1, sunk costs. 2, the Nazi Germany was a serious threat to the US and the Allies, but Japan was the US's biggest adversary, and they were showing no signs of slowing down. Well, would Japan have surrendered eventually? Well, I'm not too sure. I'll give you my guess, but first let me tell you why I think so. First, the emperor did not accept the terms that were laid down in the Potsdam Declaration. Why? Because that called for a democratic government. The emperor did not like it because he had no role in the democratic government. So my guess, having seen dictators, read about them and whatnot, no, Japan wouldn't have surrendered until it was defeated. Or the emperor had killed himself. That was the other option, but yeah, what were the odds? So to overwhelm the Japanese forces, the US bombed Hiroshima. Apparently, the proposal was to bomb it in the night so that the flash of the explosion, which was brighter than the sunlight on Earth, would have shocked them more than anything. But then they decided to do it during the day because of some logistical challenges that they had back then. Remember, we're talking 1945. Yet, oh God, Japan showed no signs of surrender. And the US said, well, I gotta drop the fat man on Nagasaki. Now, in my view, this information is enough to put Oppenheimer in context. Although I must mention that the film fully only revolves around Dr. J. Robert Oppenheimer. Whatever I've said in this episode does not prominently feature in the film, but is just alluded to or, brushed through. But all of this is important because this will help you get a better picture of what you're watching and why some things that are happening. If you have not watched the film yet, I recommend that you do because it's a brilliant piece of work. If you watch the film and not all of it made sense to you, you're in the right place. You can rewatch it if you would like, with this information in your head. Of course, you could also wait for it to come on OTT, then come back here, listen to this episode again, and watch or rewatch the film. In all, I think the Manhattan Project completely changed how we humans saw wars. Of course, though some of you might disagree, I think this would have happened regardless of which side ran the program, the Nazi side or the Allies side, because even though human stupidity is infinite, human intelligence is also a reality. But can the bombings on innocent civilians be justified? But also, can we apply today's laws, rules, and ideas and lens to what happened so long ago? That's for you to think about and come to your own conclusions. Now for a disclaimer. This episode was not recorded with reference to specific literature. I wrote it in a few hours over a weekend and based it on what I know about the war and the project. The dates and the timelines are rough estimates based on how I put them together and tried to make sense of them in my head. So, yeah, there you go. Until next time, take care. Bye.